When a network of telescopes turned toward a faint visitor from interstellar space and collected images over a 15-minute window, no one expected anything more than standard cometary behavior. Instead, the data revealed something that has left dynamicists, plasma physicists, and comet specialists equally unsettled. The object, known as 3I/ATLS, or 3IATLAS, is surrounded by an enormous system of jets on a scale and with a geometry that do not fit comfortably within our current models of how comets behave near a star. The composite image shows three major jet structures radiating from the object. Two of them form what we call antitails, sharply collimated streams of material that, in projection, point back toward the Sun rather than away from it. Each of these antitail jets extends to nearly 1 million kilometers, roughly 3 times the apparent diameter of the Moon in our sky, translated into physical size. The third jet behaves more like a classical tail, streaming away from the Sun and stretching out to an astonishing 2.85 million kilometers, about 7 times the distance between Earth and the Moon. These are not subtle features. These are macroscopic structures on a planetary scale. For context, the glowing halo, or coma, around 3I/ATLAS, measured by the Hubble Space Telescope in July, was 3 orders of magnitude smaller than these jets. The newly reported structures are roughly 1,000 times larger in linear extent than that earlier Hubble-resolved envelope. Scale alone would make this discovery noteworthy, but scale is only the beginning of the puzzle. The physical requirements to maintain such jets over time strain the limits of what we expect from a natural comet driven solely by solar heating of surface ices.
In the classical picture, as a comet approaches the Sun, sunlight warms its surface and causes volatile ices to sublimate. Solid turns directly into gas. The gas drags dust with it, creating flowing jets emanating from active regions on the nucleus. Typical flow speeds in this regime are on the order of 0.4 kilometers per second, comparable to the speed of sound in a gas at the relevant temperatures. This is a gentle process in dynamical terms, a kind of continuous evaporation powered by sunlight. Now, place that canonical model alongside the observed dimensions of the jets of 3I/ATLAS. To maintain a tail nearly 3 million kilometers long and anti-tail jets of order 1 million kilometers in the environment of the inner solar wind, the outflow cannot simply be brief flashes. The tail-like jet would require roughly 3 months of sustained ejection, the anti-tail jets at least 1 month. That immediately implies a prodigious and persistent mass loss. Here a further complication enters. The solar wind at the heliocentric distance of 3I/ATLAS flows at around 400 kilometers per second, about 1,000 times faster than the canonical sublimation outflow. Yet the anti-tail jets evidently stand against that wind, maintaining their integrity and apparent collimation, rather than being blown rapidly backward. For such structures to persist, they must be both dense and internally pressurized compared with the surrounding plasma environment.
Harvard astrophysicist Avi Loeb has calculated the implied mass loss rate needed to sustain jets of the observed scale. The result is startling, of order 50 billion tons of material per month. That is not a typographical error. 50 billion tons per month, comparable to the minimum estimated total mass of the object itself. In other words, if the standard sublimation model is correct, 3I/ATLAS is shedding matter at a rate that would exhaust a substantial fraction of its own bulk in a remarkably short time. To survive such a phase, the nucleus radius must be at least 10 kilometers, possibly more. This extreme activity, however, did not manifest itself for most of the object's trajectory into the inner solar system. Astronomers have been tracking 3I/ATLAS since July. During those months, it appeared comparatively quiescent. There was little evidence of strong non-gravitational acceleration, no dramatic outbursts, and nothing in the early photometry that hinted at what would unfold at perihelion on October 30th, 2025. Then, as the object rounded the Sun at a distance of about 0.9 astronomical units, just inside the orbit of Mars, the character of its behavior changed abruptly. Multiple jets emerged, their magnitudes and geometries unlike anything previously documented in an interstellar visitor. A straightforward explanation is that the intense heating near perihelion finally penetrated to pockets of volatile ices buried beneath an insulating crust. Once exposed, these regions could vent violently, producing extended jets whose mass flux remains high until the volatile reservoir is depleted. Comets are notorious for unpredictability. We have seen dramatic outbursts in many solar system comets when fresh ice is suddenly presented to sunlight. In that sense, a delayed onset of violent activity at perihelion is not inherently exotic.
Yet the numbers remain uncomfortable. If the jets are entirely due to sublimating ices driving outflows at 0.4 kilometers per second, the required mass loss rate is so high that the nucleus must be both very large and very loosely bound. Moreover, the antitail structures, which appear to push against the onrushing solar wind, deepen the puzzle. To reconcile these jets with thermal sublimation alone, one must invoke a finely tuned combination of geometry, timing, and internal structure that stretches plausibility. This has led Loeb and others to ask a different class of question. Suppose the jets were not mere sublimation plumes, but exhaust from some kind of propulsion or venting system. In that hypothetical scenario, the outflow velocities might be an order of magnitude higher than thermal speeds. Chemical rockets, such as those used in human spacecraft, expel gases at roughly 3 to 5 kilometers per second. Electric or ion propulsion systems can achieve exhaust speeds between 10 and 50 kilometers per second. If the jets of 3IATLAS were ejecting material at those higher velocities, the required mass loss would be 1 to 2 orders of magnitude smaller. In such a configuration, less than 1% of the object's mass might suffice as propellant to produce the observed structures. This notion moves us into speculative territory, but it does so in a quantitatively constrained way. The mathematics does not force an artificial propulsion interpretation, but it shows that our standard natural explanation demands extreme parameters. When the simplest natural model struggles, scientists are obliged to entertain additional hypotheses, including those that would once have seemed outlandish. 3IATLAS is only the third confirmed interstellar object observed passing through our solar system. The first, 1I Oumuamua in 2017, displayed its own list of anomalies: non-gravitational acceleration without detectable outgassing, an unusual inferred shape, and rotational behavior without a clear analog among known comets or asteroids. The second, 2I Borisov, looked more like a textbook comet, albeit with some peculiarities in its volatile chemistry. Now 3IATLAS arrives, seemingly occupying a category of its own.
At present, the object is receding from the Sun, and its angular separation from our star has finally grown large enough, above about 30 degrees, that Earth-based observatories can observe it in dark skies without overwhelming solar glare. Over the coming weeks, telescopes across the world will track its brightness, resolve its coma, and take spectra of its jets. The goals are clear: determine composition, measure velocities, search for fragments, and refine the orbital solution to detect any non-gravitational forces at work. Those measurements will tell us whether we are witnessing an extraordinary natural outburst or a phenomenon that challenges the boundaries of our categories. The period around perihelion contained even more surprises. In the days immediately after closest approach, observers reported not just 3 major jets, but a complex system of 7 distinct jet structures radiating from 3IATLAS. Multiple jets are not in themselves unusual. Many comets host several active regions on their surfaces. What is striking here is the arrangement, strength, and timing of these 7 outflows emerging essentially simultaneously, superimposed on a body whose prior activity had been limited. One natural interpretation is partial fragmentation. Cometary nuclei are fragile aggregates of ices mixed with dust and rock, often held together by weak self-gravity and sintered material. Thermal stresses and tidal forces near a star can crack such nuclei, producing multiple pieces that then develop their own jets. We have witnessed this vividly in comets that broke into chains of fragments, as Shoemaker-Levy 9 did before colliding with Jupiter. If 3IATLAS experienced partial breakup near perihelion, each fresh face of fractured interior could release its own plume of gas and dust, explaining the sudden appearance of multiple jets. However, the observations so far do not show a clear train of distinct large fragments separating along the orbit.
we see jets, we do not yet see multiple well-resolved nuclei diverging. Either the fragmentation, if it occurred, involved relatively small pieces, or the nucleus remains largely intact. Yet the jets appear sustained, not merely brief flashes, again implying a reservoir of volatile material and a structural configuration that can withstand substantial internal pressure without disintegrating entirely.
If we step back from fragmentation, we can ask whether there are any analogs on other worlds for such persistent localized venting. In our own solar system, moons like Enceladus and Europa demonstrate that cryovolcanism powered by internal heat sources can produce steady geysers for long periods. There, the energy comes from tidal flexing and possibly radiogenic heating. 3IATLAS, by contrast, is an unbound interstellar wanderer, not locked into resonance with a giant planet. Any internal heat source would have to be primordial or exotic. At this point, the speculative propulsion analogy becomes tempting once more. If a civilization were to design an interstellar vehicle, it might well drift quietly through interstellar space, conserving energy, and then utilize stellar encounters for navigation, course corrections, and perhaps refueling. Perihelion passages would be natural times to perform maneuvers because the craft's velocity is highest and solar energy is abundant. In that context, a sudden eruption of multiple highly collimated jets at perihelion could be viewed as vectorized thrust. To emphasize, we have no direct evidence that 3IATLAS is artificial. What we have is a set of observational anomalies that can be fit into more than one framework. The responsible scientific approach is not to leap to extraordinary conclusions, nor to dismiss uncomfortable hypotheses out of hand, but to refine our measurements so that some explanations become untenable. Several testable predictions flow from the natural and artificial scenarios. If the object has fragmented, continued high-resolution imaging should eventually reveal multiple nuclei diverging along slightly different paths, each carrying its own small coma. If the jets are purely sublimation-driven, their intensity should gradually fade as the volatile reservoirs are depleted and as heliocentric distance increases, tracing a smooth thermal response. If, however, the jets maintain unexpected coherence or shut off abruptly, we will have to look more closely at internal dynamics. Trajectory analysis is equally decisive. When a comet expels gas and dust, it experiences recoil, like a thruster firing. These non-gravitational accelerations are commonly measured in comets and can be modeled based on observed outgassing. For 3IATLAS, the question is whether the trajectory deviations inferred from precise astrometry match what would be expected from the visible jets. Any systematic mismatch between thrust implied by the jets and the actual change in motion would call for an additional explanation. A carefully timed change in direction at perihelion that cannot be accounted for by isotropic sublimation would be particularly difficult to ignore.
The story of 3I/Atlas is intertwined with another, more terrestrial story, the handling of key observational data. On October 2nd and 3rd, 2025, as the object passed within 29 million kilometers of Mars, the Mars Reconnaissance Orbiter used its HiRISE camera to image the interstellar visitor from the side at a resolution of about 30 kilometers per pixel. While Earth-based telescopes saw the comet essentially along its tail axis, Mars had a near-orthogonal vantage point. The resulting images should provide valuable information about the gross shape of the nucleus, the angular distribution of jets, and any obvious fragmentary structure shortly before the perihelion outburst. Those data are still under wraps. A government shutdown in the United States beginning October 1st effectively paralyzed NASA operations for weeks, leaving large parts of the agency understaffed or furloughed. Early retirements and budget cuts have already eroded institutional capacity. As a result, images that could have anchored our understanding of the pre-perihelion state of 3I/Atlas sit unreleased, while the object itself rapidly recedes into the outer solar system. Members of the scientific community, and even some in Congress, have publicly argued that such data, acquired with publicly funded instruments, should not be indefinitely delayed by political gridlock. The universe does not pause its dynamics while our bureaucracies sort themselves out. Meanwhile, ground-based observatories have resumed regular monitoring of 3I/Atlas. Each clear night adds photometric points, spectra, and high-resolution images to a rapidly growing archive. Combining these Earth-based observations with the yet unseen Mars side view should eventually provide a three-dimensional picture of the jet morphology. The hope is that, when the dust, perhaps quite literally, settles, we will be able to distinguish between fragmentation, unusual internal structure, and more speculative mechanisms. Beyond the immediate physical modeling of jets and trajectories, 3I/ATLAS forces us to confront questions of probability. Loeb and collaborators have examined how likely it is, under standard astrophysical assumptions, that we would encounter an object like this so early in our survey history. Their estimates start with the inferred mass of the object. From the activity levels and minimum density estimates, 3I/ATLAS must weigh at least 33 billion tons, corresponding to a diameter of roughly 5 kilometers or more, perhaps up to 10 kilometers if most of the nucleus survived perihelion. Contrast that with Oumuamua, whose mass has been estimated at only tens of millions of tons. The interstellar comet currently before us is therefore at least 1 million times more massive than the first interstellar object we detected. In any reasonable size distribution, large bodies are rarer than small ones. If interstellar space contains a continuum of debris, we expect to encounter numerous small fragments for every single large kilometer-scale object.
Loeb has explored two bounding cases. If essentially all solid interstellar mass resides in bodies no bigger than 3I/ATLAS, the probability of encountering such a massive object within the short span of our systematic surveys is less than 1 in 1,000. If, more realistically, mass is distributed across a wide range of object sizes, with comparable total mass in each logarithmic size interval, the chance drops to roughly 1 in 200,000. When one folds in the additional fact that 3I/ATLAS moves on a retrograde orbit closely aligned with the ecliptic, within about 5 degrees of the planetary plane, the combined probability of a random natural object having both this mass and this orbital configuration shrinks further, to values of order 1 in 10 million or worse. Low probabilities do not constitute proof of anything beyond the fact that an event is rare. Rare events occur, and the universe is vast. Yet in scientific inference, extremely low probabilities are a signal that our underlying model may be incomplete or wrongly specified. When you win the lottery once, you accept it as luck. When you win it several times in close succession, you look for a systemic explanation. With Oumuamua and 3I/ATLAS, we find ourselves with 2 out of 3 known interstellar visitors exhibiting strong deviations from ordinary expectations. It is fair to ask whether our model of purely natural, randomly arriving debris needs revision. Several broad classes of revision are possible. Perhaps the distribution of interstellar solid material is skewed toward larger objects, either because of formation physics in protoplanetary disks or because small fragments are preferentially ground down and removed over time. Perhaps dynamical channels exist that deliver large bodies into the solar neighborhood more efficiently than our current simulations suggest. These would be welcome refinements in our astrophysical understanding. Alternatively, the arrival of some objects on ecliptic-aligned trajectories could be non-random because they result from targeting rather than chance. If one wished to sample or traverse planetary systems, one would naturally favor trajectories that pass through the planes where most planets reside. In that context, an aligned retrograde orbit is not surprising. It is efficient. On such a hypothesis, the mass of the vehicle is not constrained by formation statistics of icy planetesimals, but by engineering requirements and available propulsion. Again, this does not mean that 3I/ATLAS is artificial. It does mean that the data we collect over the coming months and years will carry weight in debates about the prevalence and detectability of extraterrestrial technology. The Galileo project and other initiatives are beginning to build dedicated instrument networks for systematic monitoring of the sky, not only for natural meteors and near-Earth objects, but also for potential artifacts. We already know that humanity is capable of launching probes that will wander interstellar space for billions of years. It would be a parochial assumption to believe we are the first or only civilization to do so.
From a scientific perspective, the correct stance is open-minded empiricism. We design observing campaigns that can discriminate between hypotheses, we collect the best possible data, and we let the evidence decide. Spectroscopic signatures of ordinary volatiles at thermal velocities, jets that fade smoothly with heliocentric distance, fragment behavior consistent with known physics, and trajectory deviations that line up with modeled outgassing would together make a strong case for 3I/ATLAS being an unusually active but natural comet. Persistent anomalies, non-thermal velocities, unexplained accelerations, abrupt switching of jets on and off,
or structural geometry inconsistent with fractured ice and rock would compel us to look beyond. Whatever the ultimate explanation, this object is already scientifically invaluable. If it proves to be natural, it informs us that material from other stellar systems can reach our neighborhood in large, volatile-rich bodies with activity levels far beyond the median of solar system comets. That in turn constrains models of planet formation, ejection mechanisms, and the material inventory of the Milky Way. If any fraction of its behavior resists natural explanation, then we will have uncovered evidence that our universe may host technologies that traverse the interstellar medium, perhaps routinely. In the immediate future, 3IATLAS is approaching its closest distance to Earth, roughly 269 million kilometers, on December 19, 2025. From an everyday perspective, this is unimaginably far. From an astronomical standpoint, it is near enough for our best ground and space telescopes to dissect its light in detail. Juno's more distant observations in March 2026, from about 53 million kilometers, will add another vantage point. After that, the object will fade inexorably as it climbs back toward interstellar speeds and leaves our solar system forever. We are, therefore, in a race against time. A race not in the sensational sense of impending danger, but in the quieter, more profound sense of capturing as much information as possible before a unique natural experiment ends. Each spectrum, each image, each astrometric point contributes a pixel to an emerging picture. Whether that picture, in the end, shows an extreme but natural comet, a partially disrupted fragment of a distant world, or something more unexpected, it will refine our understanding of the cosmos. The larger lesson transcends any single object. For most of human history, the idea of studying visitors from other stars was confined to speculation and philosophy. Only in the last decade have our instruments become sensitive enough, our surveys broad enough, to begin detecting such wanderers in real time. 3IATLAS reminds us that when we open a new observational window, the universe rarely behaves exactly as we predicted. Anomalies are not embarrassments, they are invitations to measure more carefully, to think more deeply, and occasionally to expand our conceptual toolkit. 3IATLAS is many millions of kilometers away as you read this, a faint speck under the eyepieces of large telescopes, yet it is also very close in another sense. It brushes against our ideas of what comets are, what interstellar space contains, and what forms technology in the universe might take. Whether it is ultimately cataloged as an extreme comet, a fragmented planetoid, or a candidate artifact, the questions it raises will shape the emerging field of interstellar object astronomy. In that sense, this visitor is not merely passing through, it is leaving a lasting imprint on our scientific imagination.